Street, New York University.
From New York University, you're listening to Conversations, hosted by President Andy Hamilton. In each episode, Andy talks insight, inquiry, and imagination with a leading mind from the NYU community.
Hello, everyone. Today we welcome one of the world's most renowned climate researchers, Professor David Holland. David has published over 100 peer-reviewed papers in the field of environmental science. He is a frequent expert consultant for governmental and other organizations and often appears on the media talking about climate change. David Holland is professor of the Courant Institute of Mathematical Sciences. He's director of NYU's Environmental Fluid Dynamics Laboratory, and he's also director of the Center for Sea Level Change at NYU Abu Dhabi. He travels all over the world for his research. He has been to the Arctic 15 times, and he recently returned from his 8th expedition to Antarctica, where he conducted research that will help us all better understand the state of climate change around the world, but also, quite frankly, the fate of our planet. David, welcome.
Thank you so much for having me, President Hamilton, and it's very nice to speak with you and also to chat with a fellow scientist.
Indeed. We'll come on to science and the different approaches to science in a few moments. But David, I'd like to start, as we so often do, at the beginning. Your work, of course, is focused on very significant and important matters, the changing sea level as it affects the wider world. Many use the tools of mathematics, mathematical modeling to understand these phenomena, but you go further. You also go to the site. You go to different parts of the world, to some of the most beautiful and inhospitable parts of the world to carry out your research. So I'd love to know how you arrived at this place. And you grew up in Newfoundland, Canada, just across the Labrador Sea from Greenland. And of course, Greenland is a place where you do a great deal of your research. And I'd like to know, how much did that geographical setting in Newfoundland, those dramatic seas and skies that you must have seen every day, how did that shape your chosen profession?
I think the thing I remember most about my childhood is ice. In the sense, everything was always about ice. The summer is short in Newfoundland because it's in a northern location, but ice was ever present. And many days in school spent mostly playing ice hockey, often missing school. My mother would write notes saying I was ill and unable to attend school. The environment is very harsh. And I do remember in the summer, and always stuck with me, these very large boulders that would be found out in the barrens. And these boulders, of course, were left from the ice that had been there before, that covered Newfoundland, Canada, United Kingdom, and even New York City. So it's that fascination with the fact that our planet has all this ice. And between sports, ice hockey, and science, that was what I was interested in.
But ice could have taken you in many different directions, professional hockey player, ice sculptor, but you became a scientist. You became an environmental scientist. And David, you studied physics and mathematics at university. How did that then, in your scientific career, lead to a focus on the planet, on environmental science and the application of mathematics to that area?
So as a kid, for some reason, I was very nerdy. And I was always fascinated with the physical environment around me. And I was always curious, like many young scientists. I remember taking measuring cups and filling them with oil and water and making waves and making a mess. And doing things like that was always fun. But the thing that I remember most about that early period of my life is the moon landing and seeing that photo of Earth from space and seeing the thing on TV in the late 60s, early 70s. And like many people, I thought, wow, we live on that little ball in space. And it was very blue and very white. And that really was the most important thing that I remember of that period. I also remember my dad around that time brought home a large volume of books. It was the Encyclopedia Britannica. It was kind of the internet of that time. And I remember going through those books day and night, looking for anything about the Earth and the solar system. And I had an opportunity in a school play to play Neptune. So I had that. And but my mother always wanted me to be more of a medical doctor. I faint at the sight of blood, particularly my blood. I remember when I graduated from university, McGill, my mother told her friends that David's not a real doctor, but he's a doctor. So those are the kind of
your patient is the Earth,
yeah.
and that's a pretty significant health challenger.
Yeah.
And David, your tools in those early days were mathematics and the application of mathematics. Many would apply those mathematical models to other people's data. Why did you feel and what then inspired you both to apply the mathematical modeling techniques, but also to be collecting the data yourself?
Yeah, so the collecting of the data kind of came later. It was really first, it was the fascination with the fact that, which I still don't quite grasp, there is the natural world, and then there's the mathematical world, and there's a philosophical conversation if they're distinct. But the fact that we can represent our natural world to some extent by mathematical description has always fascinated me, and it still does today. And I remember doing those first calculations, learning how to do orbits around planets and things like that. And that was like, mathematics is so powerful in that way to understand what we see around us.
Yeah. I'd like to focus in more specific detail just on your recent exhibition and how you blend that strategy of mathematical modeling and data collection. I think you've just returned from the Thwaites glacier in Antarctica. That's an ice shelf that is sometimes referred to as the Doomsday Glacier, because if it's a huge, the size of Hungary or Portugal, and of course, if it were to break apart, it would have a very, very significant and detrimental effect on sea levels in the wider ocean. So, first of all, just to help our listeners get into this scientific issue, could you just explain exactly what an ice shelf is, and then tell us what your research found at the Thwaites glacier?
Yes, the memory of being there is still fresh. I'm only back 1 month,
Wow.
readjusting to camping here in New York City. Um, and so the actual ice shelf in places like Antarctica and Greenland, it snows every winter and the snow accumulates because it does not melt in the summer. And so a vast mountain of ice builds up the size of the United States. It's over time, it's huge. But under gravity, it flows towards the periphery and it goes out into the ocean. And the water molecule is remarkable in that its frozen state is less dense than its liquid. So ice floats on the ocean, which is really weird. I don't think any other substance in the universe does that. And there it floats on the ocean, and these ice shelves can be very large, like the size of France or anything like that. And the ocean is going underneath them, and that's where all the interaction is happening. So it's a very difficult place to get to, and it's very far away. The second thing is the ice shelf is just not a passive element in this story, but it's a doorstop. It's actually holding the ice of the continent in check. And if you remove the doorstop, then that's when it's quite possible things go haywire. And surprisingly, we've seen that in the last 2 or 3 decades, 2 or 3 places on Earth, the cork comes out and the ice behind starts to pour into the ocean.
And on this recent trip, David, what did you find? Further degradation? Are you able to detect? Are there signs of real stress on the ice shelf?
No good news there.
That's not good.
So the recent trip, it took, like many trips, it took 2 years to prepare, and we had a very solid plan to go into this Thwaites glacier, and a totally new technique approach, because there's been so many failures in the past for a number of reasons. But this time we pulled up near the Thwaites, and the sea ice was unbelievable, and we tried to cut through with our icebreaker. We cut, and it was just too thick. So we couldn't get close enough to the sea ice to get to the land ice, where we had planned to use helicopters to bring a camp in. It was just a bridge, it was too far away. So that failed. So we did a plan B and went to a neighbor site. And then we proved, with a great amount of luck, that our technique of going with an icebreaker, helicopter, and to bring all the drills and everything by helicopter and drill through the ice and check out the ocean below, which we did in the neighbor, but not on the main site. So that worked. So we were very thrilled about that. We've opened a new way to do this. At the very end, in the last few days, there was still a fair amount of fuel left. And so our very brave pilots came up with a strategy. And they said, we can, in fact, get to Thwaites, but we cannot bring a camp. We can only bring 2 scientists for a little flying tour. And I said, great, let's go check it out. It's never been seen up close. So I brought along a temperature probe with another scientist. And when we arrived at this Thwaites glacier, it was like flying through the Death Star of Star Wars. It's just so fractured and broken and channelized. And we did make a measurement. I did get a probe in, and it's the warmest water in Antarctica. It's about 4 degrees above freezing. Whoa. So the ice of that area is fractured very. I could show you some pictures and video later, but it's mind-boggling. And the water underneath it is incredibly warm. So the great ocean conveyor belt of the ocean has somehow found its way under Thwaites.
Yeah. And so presumably now accelerating, because it's a higher temperature than freezing, accelerating the whole process of fracturing and channel forming.
That's exactly right. And that's the cutting edge of our knowledge, but that's the hypothesis.
David, you use the metaphor of a cork in a bottle and the loss of the cork and then allowing the land ice to be exposed clearly to water at temperatures above freezing, which then accelerates its degradation. I want to just quote a recent UN Intergovernmental Panel on Climate Change, which included the sentence, unchecked greenhouse gas emissions will raise sea levels several feet, swallowing small island nations and overwhelming even the world's wealthiest coastal regions. Obviously, you are looking at the very forefront and the origin of that potential sea level rise. You know, as a scientist who obviously deals in data and measurement, but you must think down the road and think about what would happen in the wider world if the cork comes seriously detached from the bottle. What do you think the consequence of that sea level rise would be in coastal regions? And there's nowhere more coastal or proximal to the sea than the city that we are both in right now, New York City. Give us a sense, and those listening a sense of what you would see happening in a place like New York and other coastal regions.
So the sentence from the UN is, I think it's documents like that, I think, are the ones that have a lot of weight to them. And I have a slightly different take, but I really gravitate towards documents that a consensus of scientists put together. And in this case, the statement is it will raise sea level unchecked. I think what they mean is will likely.
Yeah.
It's a bit too certain, um, but it's almost certainly true. And what it is that the reason I pause is because in my mind, I see firsthand from theory and from observation consistency with that statement. And what I don't see though yet is that we've really put in the scientific effort to really make it as solid as we would like. I think we are all doing our best to do the science, but there's so much more to be done because it's possible that this glacier called Thwaites will not go unstable, that the sea level around the planet will not change.
Okay.
It's more likely that it's going to be far worse than the statement made by the UN that Thwaites is going to go and it's going to take out its two big neighbors and the whole thing is going to fall apart. And so it's in that territory that you and I as scientists speak a little broader and less specific than if I give my nuance between their statement. So if I was to go a really short statement, I'd go with theirs.
I understand, and inevitably part of the challenge of science is that we measure, we hypothesize, but ultimately, until further data comes in, we cannot be certain of the future, of the outcome of any particular change. But preparation and behavioral change so that we don't continue that accelerated greenhouse gas emission is clearly a desirable thing for all to do. We'll come back to that in a few moments.
And I could add to this also is that not so long ago, 10,000 years ago, when we look at the record, there are periods when sea level goes up by tens of feet per 100 year for several hundred years, like 100. It's an enormous raise in sea level that we've seen. It seems to come out of Antarctica. And so the whole thing is very non-periodic. It's very surprising when these things happen. And I think our modeling skills are mathematical. Our models need to learn more about abruptness. Right now, they're a bit too smooth. So going forward, if you're asking about the impact, this would rewrite the global coastline. Places like Florida would probably be gone. And things of that nature. And there's also the ecological factors of salinity going over beaches and all that. So it's all very not so great. And the final thought I was having on that is about a decade ago, I was in this apartment and we had Hurricane Sandy. And that was a 1, 2, 3 punch. The sea level, the storm was big, the tide was big. So this raising of the global sea level by melting ice is only going to make things like that even more likely. So we don't want to pile on all the bad things, but there are a number of things to think about here.
I'd like to come back to science and the nature of scientific inquiry, and obviously you've touched upon, David, your work in the Antarctic and the Arctic and the way in which you collaborate and have many scientists at the different sites and helicopter pilots and the people who allow research to be done. And of course, in your case, you have a very important collaboration, which is with your wife, Denise. And marriage is a partnership in every sense of the word. And so I'd be fascinated to hear how collaboration allows you to do what you do, not just with Denise, but also with presumably the international teams of scientists who are in the different locations measuring and calculating.
So these places are challenging because of the presence of ice in the ocean and on the land. And I can provide perhaps a few examples. And there's also life in these places. And you would think, well, polar bears, of course, are very strong. But it's actually the mosquitoes that will have defeated many a person in Greenland. We've had researchers go in their tents and not want to come back out. Just these swarms of mosquitoes.
Yeah.
The on the ocean, the ice, the dangers. We had a couple of years ago. Our captain was bringing a boat from Iceland to us, and on way, he got caught in the sea ice, and then his boat sank, and he was rescued by search and rescue, but he got out just alive with his family, and very lucky. So it's even in today's day and age, nature, of course, rules north and south. Um, I also find flying in helicopters very exciting and very scary.
Yeah.
The helicopters we have are twin engine, and more than once there's been problems with one engine. When you smell in the cabin, you smell this burning smoke. It's like, well, that's not good. And on the ice itself, it's very dangerous. We've lost a handful of people. 2 or 3 years ago, one of the people we had visit here at NYU to give a science exhibit near our camp in Greenland. He went walkabout to check his weather station and was never seen again.
My goodness.
Yeah, so it's people. It's a very unforgiving landscape and environment.
Which presumably means preparation and safety protocols must be
Yeah,
constantly uppermost in your mind.
it is, and always the people getting hurt are the most experienced.
Yeah. Because they become complacent. I think
Yeah.
that's a sobering lesson for all of us. Just on in that vein, David, that there is such a rich history in of journeys and expeditions to the Arctic and the Antarctic. I grew up in Britain, and every British child it learns the story of Captain Scott and his expedition, and of course. Oates, who went out of the tent. I will be some time, and that heroism, and of course, very recently we've had the headlines of the discovery of Sir Ernest Shackleton's ship, the Endurance, which sank, I think, a little over 100 years ago in the Weddell Sea, just near the Antarctic Peninsula. I'd be fascinated to hear from you how much the history and the legacy of exploration has played both in your career, but also as an inspiration or a set of examples and lessons to help guide your own work and your own travels.
A very specific decision to do a PhD in studying sea ice at McGill University actually came out of learning about the Franklin expedition in the high north. And that story launched the entire accidental exploration in looking for Franklin. All of the north was discovered. It's like as people went around. And so it's those kind of, in that heroic age of polar exploration, north and south, that really captivated me, and that really set me up to want to understand that.
Yeah.
The My summer home with Denise is up north in Canada in a small fishing village, and in that village, which used to be big in Arctic in the past, there was a Captain Bob Bartlett, and he was famous because he knew how to navigate ice like no one else on Earth. And so Robert Peary, the American, asked Bartlett to take him, and so Peary went off to the North Pole with that capability. And so later in his life, Bartlett became very much interested in doing research in Greenland, which was quite remarkable as he became older, and sought support to do that. And so Denise and I kind of feel like we were following in his footsteps in some small sense, and his house is just a stone throw away from where we live now. So it's a very nice feeling to be connected to that part, that past.
When you tell stories, and obviously of figures of characters in the history of Arctic exploration, it brings us to the topic of communication. And earlier in the conversation, David, you touched upon the complexity of science and the uncertainty of science. Yet, obviously, we're living in a world at the moment with a great deal of necessary focus on climate change and on greenhouse gas emissions. How do you think, and in as you communicate your own work beyond the specificity and the detail of scientific journals and rigorous scientific publications, how do you think about communicating the what we know and what we don't know, and how we should all be thinking about that impact on the future, extrapolation to a future, and because ultimately, of course, this also then any discussion around climate change inevitably also falls into political realms as well. So as an active and very prominent scientist, how do you think about are you cautious with your words, or are you more out there and forceful with your words?
I think both.
a fine answer.
The in Antarctica, the U.S. Congress people were there, and it was interesting to watch how scientists share science with the Congress. And some scientists give some very long answers that don't go very far. It's just interesting. For me, the way I think about science outreach is kind of a little bit similar to education. And I established a lab on the corner of Mercer and Washington that you probably walked by. And that's all about a 1 meter scale rotating Earth, so that on that table, I can mimic, for example, a phenomenon like the Gulf Stream in the ocean. And you get to see it with your eyes and with lasers and dyes, and it's a very real experience. And you don't yet need the math or anything. You can just say, I can see that phenomena as it is on the real planet. So there's this real sense of letting people see the answer themselves, if you will, of what is something, rather pointing the way rather than the telling of the way.
Yeah. And to create that sounds like almost creating an opportunity for us all to be an Apollo 11 astronaut, to come away from the Earth and see, with scientific data driving the model, what is happening to the ice caps, and also presumably the various ocean flows.
Absolutely. And so that's exactly the approach that I take in my science, is exactly what you just said. And you put it very elegantly. I hadn't even thought about that myself, in that Apollo framework of looking back at the Earth. And really, that's what the model Earth is in the lab, the physical one. But in a more abstract way, the mathematical model is that too.
Yeah. Apollo 11, not Apollo 13, where it went wrong. Yeah. But David, your career has been a remarkable one, a very important one. I want to take this opportunity, with many people listening, to congratulate you. You were recently made a fellow of the American Geophysical Union in recognition of your work. And as someone, very much still in the middle of your scientific career, you must also look to the future of scientific questions and scientific challenges. And my next question is about the future of your work, and what do you see as the next challenge for you in terms of the mystery of how the Earth works and how the Earth is changing? And will it take a different form? Will it take a different geographical location? What is exciting you at the moment about future study?
So leading up to now, what's been exciting is this sense of discovery about how our planet works. As an individual person, when you see something, you can see it theoretically, but when you see it actually in data, in nature, and it's real, that's what I think all scientists find really engaging. And we kind of do it because it's fun and we love that. So for this part about the thing called melting ice, when I started out on this, I had no idea where that was going. You would kind of think you warm the planet and the ice melts because the air is warm. But it turns out the whole discovery was rather in a weird loop. It's the air temperature changes the wind changes the ocean currents, like the Gulf Stream. It doesn't warm the ocean, it just needs to change the currents, and then the ice sheets light up. So it's that kind of pathway. The wind blows and the ocean goes. That is what has been seen in data, and that I saw in a model before I saw it in data. Normally it's the other way around, but it's really the way the planet works. And what I find is none of it is intuitive. None of it would you guess. It's kind of, I think our minds are best suited to do math, physics, and observations. Putting together the complexity of how the planet works is something you just have to observe, see, and then memorize, but you're not going to guess it.
Yeah, David, that's fascinating. We're coming towards the end of our time, and I'd like to ask a last question on more of a philosophical note. And you've talked about the conducting of your research on in the Arctic or in the Antarctic. You've talked about some of the dangers, the safety concerns that you have, but there must be sublime moments out, as you said, for many weeks, often in the wilderness, far from any civilization, and on some of those long days and nights, presumably with magnificent stars and aurora borealis from time to time. I'd love to know what goes through your mind as it relates to the planet. You are seeing something that few others see, the solitude, but also the enormity of the landscape, and how that speaks to you, and how you react to it.
There's the up and the down part of that.
There usually is to most things, including those mosquitoes you were describing.
And the ups and downs are absolutely extreme. It's something you don't experience here in New York City in either direction. And it's kind of waking up in the tent in the morning, and the boots are frozen, the gloves are frozen, toothpaste is frozen, sunblock is frozen. One morning I decided to go and fry my gloves, and I said, I have to warm these up. That was a real breakthrough. There's everything you plan in the lab here, equipment, get it ready. It all works in New York. Nothing works when you take it to the field. Everything that could go wrong goes wrong. So there's all that moments of frustration and like, why am I here? And there are those other extreme moments that you pointed to that I've never felt any other time in my life, when you realize it's just you and a pilot, and you're the only people who've ever been to this part of the planet. Nobody has ever seen this. Nobody's ever been here. And it's just, you're speechless. And it's that sensation inside you that actually counteracts everything else manyfold. And it's again a little bit like looked like the moon, and always makes me think of the moon. And the moon always makes me think how fragile this piece of the earth, so far away. And then when you're there, you say, well, this is all we have. There is no more earth. This is the end of it, literally at the bottom.
Yeah.
And so it's that sense of, my gosh, this planet's so finite, and it's so easy to trigger it into unknown responses.
David, this has been a wonderful conversation, and I want to thank you. I think you've talked about the challenges that the world faces. You've talked about the way in which you carry out your research and this linking of the mathematics with data collection. But I think your last comment also for me reinforced that very nature of doing experimental science. That wonderful quote from Einstein, 99% perspiration, 1% inspiration, and frying gloves and walking out into swarms of mosquitoes. It's different in every form of science. My world of chemistry the mundane, the difficult of getting experiments to work, of having experiments fail, of having equipment break. This is the reality of science, and of course, it's the necessary pathway to discovery, to exploration and discovery. And you work in a world that your discovery is critical for the world, and it's critical for all of us to help navigate the next steps in the life of this planet that we all share. So, David, it's been really fascinating to talk to you. Thank you for being with us today.
Thank you so much, President Hamilton. And there's an open invitation for you to join us in Greenland anytime you like.
Oh, you're on. As long as I bring mosquito repellent, I will join you. Thank you, David, very much indeed.